we just went through a little intro to week 5. In the last lecture, I introduced some of the speakers who are going to be talking here when I'm away. We also went through this ethanol combustion reaction. I showed you how to do it pictorially as well as algebraically, and then how to go back and check your work. So let's see what else is going on. In week 5, this is it's listed as the resource base. And I did a little bit of Shramsky in here before, didn't I? Yeah, I want to. Yeah, let me show you. Okay, and I will post this paper because it is incredibly important. I'm having a hard time overemphasizing the importance of this paper. So if we go down here. Shramsky, 2015, and just remind me if we've gone over this before, because this is he just calls it the biosphere, and he shows, and we just made the joke that the Earth has humans. So here we are, humankind draining the chemical battery that's been charging for the last 2 to 3 billion years. That's just kind of a pictograph. But then if you look into the data, in fact, I can't think of a better paper to review than this thing for the resource. This is week 5. Here's the resource. So when we were in NRGY 101, we talked about that 500 exajoules per year that humanity consumes. That number is mentioned. This whole thing right here, 2,000 zetajoules plus 500 zetajoules plus 40 zetajoules plus 35 zetajoules. Let's just for fun, so we can wrap our heads around these numbers, see how big that number is. So let's just do that really quick. We have not talked zeta. But there's 1,000 X's in a zeta. Okay. There's 1,000 X's in a zeta. Yeah. Been waiting to do some Shramsky. Oh, and meanwhile, let's put the energy technology program into moratorium so nobody gets this information. Sorry, no, that was my slightly maniacal laugh. We're broadcasting live from Missoula, Montana. So let's do this math. 2,000 plus 500 plus 40 plus 35. Let's just run that. I think I can do that in my head. Let's just try 2, 5, 7, 5 zeta joules. Okay, that is all of the energy on planet Earth, which includes the non-recoverable. And this is stuff. I mean, this is a little bit where you have to spend $1 worth of energy to pick up a penny. Sure. That's what non-recoverable means. That would mean you'd have to dive down to the bottom of the ocean and pick up, actual plankton crap and bring it up and then set it on fire. It's not. I mean, sure. So that's non-recoverable. 2,000 then. This 500 is the nuclear, and then this 40. 40 plus 35, let's look at that breakdown a little bit. What's the 40? That's 35, 30, all bio energy. Okay, let's just first look at this 35. This was all of the bioenergy available on the Earth 2,000 years ago. In 1900, there's still 23 zetajoules left. In 2000, there's still 19. This 2 zetajoules is, that's how much gets replaced each year. That's what the, Mother Nature puts in the bank. I'm still trying to figure out what that 40 is. Oh, yeah, there we go. There's the 40. The 40 is the recoverable fossil fuel potential. So that's kind of what's still in the bank. And it's not exactly clear to me why he is counting the recoverable fossil fuel potential different from the bioenergy. I want to take a look at that really quick. Let's just look at the distinction. I'm just going to look for the number 40. Okay, let's read here. Despite some excellent sobering analyses of the present use and future prospects of fossil fuels, so that's kind of back to our peak oil kind of deal, the magnitude of the remaining economically recoverable hydrocarbon energy store is subject to much debate. In Figure 2, we acknowledge the uncertainty by assigning a conservative value of 40. So he's basically he's basically doubling his bet. He's like, maybe there's twice as much there as we think there are. And that's, so getting from 35 to 40. That's how I'm reading that. That's how I'm reading that. Okay, so that's where that 40 is coming from. It's like, okay, guys, we'll give it to you. You know, okay, so there's not 150 years left. There's 300 years left. Fine, but it's still a drop in the bucket. Is kind of the point here. Sure. Okay. So there's our 2575. Now, let's just say theoretically all of that were usable. Let's see how many years that would be, because right now 500 exajoules equals 0.5 zetajoules. And I'm going to triple check myself on that. Orders of magnitude, powers of 10. Might be kind of fun. Yeah, there it is. I was saying zeta, but it's zeta. I think at the other end there's zepto. But yeah, so 10 to the 21st. So what I wrote is correct. 500 exajoules is 0.5 zetajoules. So if you look at that number, we could basically double it. So if we take 75 times 2 equals, so 5,000 years of live long and prosper at our current rate of consumption. But that's not the case. There are between this well, and let's just leave nuclear out of it for now, and so let's just look at biomass, because that's where the majority of our energy comes from. And so there we're talking 40 plus 35. Well, that's just 75. Double it, it's 150 years. And it's the same exact number that we got on the very first day of NRGY 101 when I said, how many years left do we have? Well, there it is, at our current rate of consumption. Okay. So let's read on with Shramsky. So that's kind of the big picture on bioenergy on planet Earth. Okay, so there's your 35 that was just mentioned. That was the year 0, 2016 years ago. Here is 1,000 years ago. I think he mentioned 26 or so. And, here we are at the year 2000 with 19. Now, look at that curve. It's not a happy curve. So do some extrapolation. I know we've all had 101 and 102. You tell me, do you use a linear regression? Do you use an exponential, parabolic? In this case, that looks like a parabolic or even hyperbolic curve to me. So that's the forecast. Now here's the next one. Here's our population. Here is our consumption, and this is the ratio between population and consumption. And what it's telling us is that each one of us are running at about 2 kilowatts, that's the number that came out when we had, each one of us has 20 techno slaves, one human power is 100 watts, and we're all running at an average of 2,000, so there that is. But it's in decline. And it's in decline either because we're becoming more efficient, or there's less, or people are just doing without. And the answer is it's one of those three. Some people are doing without. They can't afford it. They can't access it. I like to think that some people are becoming more energy efficient. You hear, people living in cities getting rid of their cars, taking public transportation, eating locally, et cetera, et cetera. So that's where why this curve is down. So, on the one hand, you're like, gosh, that's good news. We're becoming more efficient. The other one is like, gosh, is this actually some kind of collapse that's occurring in terms of our energy consumption? And then this guy is pretty telling as well. And this is not that easy to interpret at first, but let's just take a look at it. He's calling this constant, or this variable, more appropriately variable, omega, as the number of years of remaining bioenergy at the current rate of consumption. So, for example, if in the year 0, the human population did not increase and each person just used the same amount of bioenergy as the previous year, we would have had 65,000 years of energy, which is even more than this 5,000 or whatever we hopped into a second ago. There were, I don't know exactly what happened. I don't know if this was a war or famine or what. This was the plague. So there's just, fewer people. Yeah, and you've got a little bit of forest recovery right here. So the forests are growing back. We zoom in, and here we are in 1960 with 1,800 years left, 1,500, 1,200, 1,000 years left at the current rate. So again, the one bit of good news that I can see on this curve is that it's flattening, for lack of a better word. And whether that's more efficiency or people are going without, it's not clear. There's probably some combination thereof. Now, why is that at 1,000 and not that 150 that I just showed you? Well, because he's including the nuclear as well. He's including the nuclear as well. Okay. So, and then the logic presented above is indisputable because the laws of thermodynamics are absolute and inviolate. We've studied them in detail. Unless phytomass stores stabilize, human civilization is unstable. The battery paradigm highlights the need to continue to refine estimates of global biomass degradation and its corresponding chemical energy contents and of recoverable fossil fuels. It emphasizes the need for greater recognition of the central importance of living biomass and the past, present, and future trajectory of decreasing omega. And omega is basically just how many years there are left. History offers a mixed message about the capacity of humans to innovate and act in time to avoid collapse. At local and regional scales, many multiple past civilizations failed to adapt to changing social and ecological conditions and crashed catastrophically. At the same time, human ingenuity and technological innovations allowed the global population economy to grow at near exponential rates. I'm pretty stoked to go see Japan. I don't know if you've read the book, Collapse or not. If you haven't, take a look at it. I read it, I think the year it came out in 2006. I guess it's out in paperback now. It's only $12. I've been pen pals with Jared Diamond back and forth over the years a little bit. In fact, there's a faculty member on main campus who works for the Natural History Museum in New York, who has co-authored some papers with Diamond, and he's written extensively about Montana. Diamond talks about how Japan did not suffer the same fate that Easter Island did, for example. Japan was forward-thinking enough to actually put a real value on its remaining biomass to the point where every tree ended up numbered, labeled, and set to some specific task. I mean, it was a little bit draconian, but on the other hand, Japan could have become Haiti, sure, right? Japan could have just mowed the place down and turned into Haiti. I also know Japan is very stickler on recycling. They've got that thing just down to a science. Everything gets kind of put back into their.
It's punishable. It's findable.
Oh really? Yeah. Okay. But I don't know if I'm going to test that. Just throw my big old latte in the garbage here. See what happens.
It's pretty amazing how quickly those citations get.
Yeah, I've heard it's very tidy, very neat. So I'm looking forward to seeing that. Anyway, so Diamond, like Shramsky, says. Yeah, there's some darker sides here, but there's also some bright, there's some positive examples to look forward to. And here he goes, talking about animal, hydro, wind, wood, coal, oil, natural gas, nuclear, photovoltaic, solar, geothermal, and others. I'll just wrap up this little page and go from there. The implications of past localized collapses and global growth are of questionable relevance to the situation, however, now, because for the first time in history, humanity is facing a global chemical energy limit. The Earth space, and again, I want to reemphasize that this little 2 zetajoules, that's everything that's pumped into the biosphere. That's the amount of energy that the Earth's biosphere is able to convert from electromagnetic energy into chemical energy. That's why he's got that little blue wave here. So if you look, well, maybe that's pretty good news, because if we're only using half a zettajoule per year and Mother Nature is providing 2, maybe. Yeah.
That's theoretically been happening until now, right?
Yeah.
So.
Yeah. The question is, well, gosh, does that mean that the oldest tree that we're going to see pretty soon is 4 years old? Because anyway, that's the implication. The oldest bioenergy might be only 4 years because we're consuming it at a rate a quarter of which Mother Nature is providing it.
Maybe the only thing that will be left at some point will be just that immediately replenished.
Yeah, which I find pretty repulsive. I know, I've heard that Norway and Brazil have decided just to keep their fossil fuels in the ground for future generations.
Yep.
Yeah. So.
Yeah. Does he talk about the correlation between just population increase for, because obviously within population has really increased.
Yep,
So of course we're going to be using more energy
Yep.
due to that.
yep.
So, you know, does that go into, does he talk about that? You know?
He does, yeah. I think that really is the main point of this curve right here, is to say that
It's that green one.
yeah, it is. So this is what you know, the human population has been doing. This is how quickly we consume energy, and then yeah, the implication is if we're gonna keep doing this, we can't. I mean, there's just we can't keep doing that. Like the red line cannot go up anymore. It's just not there. So the green line has to go down. Does that answer your question? I mean, I think that's just kind of
Match those two.
yeah. So the question is, where does what does our energy profile look like?
It'd have to be a pretty steep curve on that per capita use to match that growth curve, you know, because that's crazy. Growth curve. It's just nothing but up.
And you know, it's taking into account, you know, green's going down because people are actually not going to live as long.
I don't know, but it has. I don't.
Crappy GMOs.
No, I don't. I'm not. So again, I don't think the green line heading down necessarily correlates with lifespan. It just means maybe you just don't go on as many trips and buy as many big cars and throw as much food in the garbage and.
I've heard with all the energy efficiency efforts, like the little ones that we've been making collectively, just as far as even just lights in your house,
Yeah.
energy efficient appliances, it actually has taken our per capita use down.
Yep.
I know refrigerator is the big one.
Mm-hmm.
Just in the last, 10 years, refrigerator
Yep.
is substantially
Yeah.
better.
Yeah. So I tend to look on the bright side and say, hey, let's just be more efficient with our energy. You know, put the solar thermal up, for example. So, and I like this. So living biomass is the energy capital that runs the biosphere and supports the human population and the economy. Urgent need not only to halt the depletion of this capital, but to move as rapidly as possible towards an approximate equilibrium between, I think NPP is net vital mass production and respiration. There is simply no reserve tank of biomass for planet Earth. The laws of thermodynamics have no mercy. Equilibrium is inhospitable, sterile, and final. Yeah. So
That's quite the summary on that.
Yeah.
That's good stuff.
yeah. So anyway, these guys I'm sure have been working on this project for quite some time. Usually they will say where they're.
You said it was published 2015?
Yeah, it just came out. Let's see where their funding came from. Acknowledgements. Yeah, so National Science Foundation, Macro Systems Biology Grant.
Awesome.
Yeah. So all of this is peer reviewed. Everybody looks at it, and there it is. Okay, let's just see what else we got in the shell, because in my mind, I mean that is really the most recent and accurate paper we have on our resource base. And I think that came out, well, very recently. Let's look at the reading assignment. Textbook chapter 3. Yeah, take a look at chapter 3. I think you can get through this pretty easily. What he's looking at, what we're looking at in chapter 3 are the higher heating value versus the lower heating value, and let me show you the distinction between that. HHV versus LHV. I don't mind using the wiki on this one. Okay, higher heating value, pre-combustion temperature. And you've probably seen this a lot. If you've gone and looked at roof lines lately, you'll see that houses are going from a big old stack like this to a smaller stack. And these are typically called condensing boilers. And so what typically happens, so I'm just going to do with lower heating value, what happens is your hydrocarbons come in, your oxygen comes in, fire happens. Need a better pen than that. Fire happens. Combustion products go up. And typically what you're looking at here out the top is still kind of a high temperature. So if you put your hand up there, you're going to feel it. So a lot of the energy goes up the stack. So your overall efficiency goes down. In the case of higher heating value, basically the same thing is still going on. You've got your CH and your O2 coming in. Heat goes up, but in the condensing boilers, the water vapor, and remember water vapor is one of the main components in combustion, the water vapor actually comes back down as it condensates. So as it rises, it cools, and then that heat and let me just, so it's kind of cooler up top, and your heat stays more in the house. So that's the difference between higher heating value and lower heating value. Did the products, as it says here, did the products reaching the original pre-combustion temperature? So did that water, did that CO2 come back to whatever the ambient temperature was? Yes, exactly. More complete energy exchange, exactly. Okay. So that's what you're looking at when you're looking at the HHV in table 3.3, thermochemical properties of selected biomass. You'll also notice that there's a little bit of sulfur. Where's the sulfur coming from? Well, it's coming from the fact that we're looking at biomass. So let me show you where that's coming from. So amino acids are the proteins that make up all living matter, and if we burn it, one of the amino acids here, so glycine, alanine, serine, threonine, cysteine, valine, leucine, isoleucine, methionine, proline, phenylalanine, tyrosine, tryptophan, aspartic acid, glutamic acid, asparagine acid, glutamate, histidine, lysine. Okay, where did you go? Oh, there you are. Cysteine. Cysteine right up here has a sulfur as one of its side chains. So that's where the sulfurs are coming from when you're looking through this table 3.3. I don't see phosphorus on here, which is a little bit surprising because there's a phosphorus in the DNA backbone. Maybe that's what's just included in ash.
Sure. It is kind of phosphorus.
Yeah, because you typically don't see the phosphorus as a combustion reactant in most of these. Maybe it's just sticking around the ash. There's a little bit of chloride. I mean, almost any living organism has chloride channels, and God, I love looking at this stuff too. So this is kind of wild. I mean, you're like, oh, what are we setting on fire? Oh, we're setting these molecular acids on fire. So right down at the cellular. So we're looking at the cellular level. and you've got trillions of cells in your body, same thing with plants. This is the cell membrane, and this is a protein. There's all those amino acids that we were just looking at that allows individual chloride ions to pass in and out of cell structures. If this is messed up in the human genome, you've got cystic fibrosis because you're not pumping chloride, but there's your chloride content. So all of this are biologically relevant elements. But those are the main ones: carbon, hydrogen, oxygen, nitrogen, sulfur, and a little bit of chloride. Yeah, so that's what you're thinking about. Looking through chapter 3. With this week 5, we looked all the way up at the big picture of all of the renewable resources on Earth, and we took it right down to the atomic level of what are in these individual atoms and molecules that we are setting on fire to make energy. So,
Awesome.
yeah. I love this course. Thank you, Brian Kearns. Yeah. Guys, and one more thing. I don't know how many hits. Most of these YouTube videos don't get much. But we are in a situation right now where the dean is pushing to put the energy technology program into a moratorium. And it's a little weird. I think, and I would love to look at the numbers, but I really think that I've graduated more students with energy technology majors in the last 5 or 6 years than the chemistry department has graduated. And so, are we putting the chemistry department? And no, and to be fair, what we are doing is we've moved our building energy efficiency, merged it with John Freer's Green Building Energy over on West Campus. We are merging some of our courses already, ETEC 214 with the pre-engineering program on main campus. We're still very strongly partnered with climate change, so Nikki Fear is working on recruiting her climate change students to take NRGY 102, to take the practicum, all that good stuff. And we've rewritten the requirements for the certificate. And so what we're really hoping to do right now, this is my little plan for moving forward, is to say, okay, well, I'll meet you halfway and put the associate's degree in moratorium, meaning that we're not going to accept new degree candidates for the associate's degree. Fine. We will accept degree candidates for the certificate. Come in, 15, 20 students in 101 in the fall. And then we've got, depending on attrition, 10 to 15 grads in the spring. And okay, so we're not graduating 25 nurses every year, 25 welders every year, but I think we're graduating some very high quality, well-informed folks that can go out and, make a difference in these fields.
So too, I think the quality of the education that we have in this program has been excellent.
Yeah.
It's challenging, but it's supposed to be.
Yeah, it is.
That's the point.
It is a challenging program, yeah.
I'm here to not learn.
Yeah, yeah. So another thing you can do also is, current students, and I've got alumni as well, write a letter, and the people to write them to are, and I can just write their names down. These are the folks that matter. Are Dean Shannon O'Brien. I don't know if I spell. Is it EI or IE? I'm never going to remember O'Brien. IEN. Okay. There's also Provost Perry Brown. And I'm going to sit down with Perry and Shannon in a couple weeks and talk about how we might merge or share resources with pre-engineering. President Royce Ingstrom. And also Commissioner Clay, Christian. And I think you'd be hard-pressed to, for any one of these four individuals to say, we don't need a renewable energy technology program in the state of Montana, because frankly, we're the only one left. You know, there was like a wind thing for a while and a biomass thing for a while, but we're kind of it for the state of Montana. And if you go out and look, sorry, one more thing. I'm just going to like show you how important and critical I really think we are. So NSF ATE centers. So this is the National Science Foundation. That's where we are. Yeah.
Right in the middle.
That's why I popped my grant out. But let's look at programs.
Yeah. That's astounding.
Let's look at projects. Map. ATE Central. Let's just take one. Here we go. Okay, here's centers and projects. This is the map I was looking for. Let's just zoom out a little bit so we can see. So there's one here, and there's one at Flathead Valley Community College. These are so the one we saw before are the centers, you know, the real hubs, but there is not, maybe something in North Dakota, maybe something in South Dakota, nothing in Wyoming, a few in Idaho. I mean, we're it for Montana.
I mean, that's, talk about an underserved population.
Yeah. So, you know,
That whole section has just a very small percentage.
yeah, and granted, there aren't that many folks out here, but I mean, we're basically, you know, serving a pretty big pretty big region here.
Yeah, absolutely.
Yeah, projects. Okay, so keeping it alive. Anyway, so thanks. So yeah, these are the folks to, you know, write your own story to. Why you think it's important to keep the program alive, and maybe we'll get an ear. All right. Well, next time I'll see you a couple weeks from now. I'll send a postcard or listen an email from Japan. Yeah. Thanks. Thanks a lot.